You've probably been here before. You write a loop in Python, it looks clean and it makes sense. You understand every line that you have written in your program. You hit the run expecting it to finish quickly and it doesn't. The program just sits there. The CPU spins, the fan turns on, and you start wondering what you did wrong. So you try something else. You rewrite the same computation using NumPy. You don't change the math, you don't change the result, and you barely change the code. And yet suddenly it's fast, 10 times faster than your previous code, sometimes even 100 times faster. This creates a very natural desire. You want to understand why. And now you're wondering why it's happening. But what actually changed? What did Python do wrong? And what is NumPy doing so differently? The conflict starts when you realize something uncomfortable. The algorithm didn't change, the logic didn't change, the math didn't change, and yet the performance is completely different. That means the explanation cannot be about math. It has to be about execution. Let's slow this down and make it very concrete. Here's a plain Python loop that adds numbers together. Nothing fancy, it's just a counter and addition. When you look at this code, it feels trivial. One addition per iteration, and that's what your brain sees. But that's not actually Python sees. Python does not see add two numbers. Python sees add two objects, and that difference is everything. Now here's the NumPy version. Same math, same result, but the execution path is completely different. This is where many people reach for an explanation like Python is interpreted or NumPy is written in C. Those statements are not wrong, but they don't explain the real issue here. The real conflict is that Python pays a cost for every single element. NumPy doesn't. Let's zoom in on just one iteration of the Python loop. When Python executes total plus equal I, it is not performing a simple CPU instruction. It is performing a sequence of decisions. Python checks what total is and it checks what I is. It figures out which addition operation applies. It creates a brand new integer object for the result. And then it updates the reference. All of that happens once. And then it happens again and again 10 millions of times. You can see a small hint of this behavior if you look at the object identities. The value increases by 1, but the identity changes every time. That's because Python integers are immutable objects. You are not modifying a number, you are constantly creating a new ones. It's not a bug, it's a design choice. It makes Python flexible and safe. But it also means that a simple loop hides a huge amount of work. This is the core conflict. Python is doing far more than math you ask for. Now watch what changes with NumPy. When you call some function for the NumPy array, Python does almost nothing. It hands control to compile code and steps aside. There is no Python loop. There are no Python integers involved in the inner computation. Inside that compile code, the loop is simple. It works through the memory and adds values together. No object creations, no type checks, and no dynamic decisions, just numbers and memory. And this is the change, and this is the moment where everything flips. Python thinks in terms of objects, but NumPy thinks in terms of memory. And modern CPUs are extremely good at processing memory in long predictable streams. This also explains a common trap that confuses people. These two lines return the same result, but they don't behave the same way. Some array pulls value out of the NumPy array one by one and turns them into Python objects. That drags the entire computation back to Python's object model. Array.sum, however, stays in compile code from start to finish. Nothing about math changes, only where the loop runs. At this point, the conflict deepens. If NumPy is so fast, why isn't it always faster? The answer is cost. NumPy pays an upfront cost. It allocates array. It prepares the operation. It crosses the boundary into compile code. That cost is fixed. Python pays a per element cost. Every iteration carries overhead. You can see when you compare small and large workloads. For small data, the overhead dominates and the difference is small. For large data, however, Python's per element cost explodes, while NumPy's cost stays flat. This leads us to the result. NumPy is not fast because it's clever. It's fast because it refuses to do work per element in Python. It moves the loop into a place where CPU can operate directly on the memory. It replaces millions of dynamic decisions with one predictable pass over contiguous data. Once you see this, performance stops feeling mysterious. You stop asking why is NumPy faster and start asking where is the loop running, and that the question leads to the next one. If NumPy gets its speed from the memory, then what exactly is NumPy array? What does it store? Why does layout matter so much? Why can slicing be free? Why do views exist? Those are not random details. They are the foundation. That's what we will open up next. In the next episode, we are going to look directly at the memory model behind NumPy array. Until the next video, good morning, good afternoon, and good evening. Bye.